Hello everyone, my name is Jessica Murphy. I am a second, almost third year occupational therapy student at the University of Alberta at the Calgary campus. Over an 8-month period last year, I assisted in conducting some research on a new cargo management system, the RazerLift, as a Mitacs research intern. The principal investigator on our team is Dr. Antonio Miguel Cruz. Our team also included Avneet Chauhan, a student like myself, Dr. Adriana Rios-Rincon, an assistant professor at the U of A, and Dr. Lily Liu, Dean and Professor of Applied Health Sciences at the University of Waterloo. Manual lifting of portable ladders on and off of work and service vehicles is a regularly performed job duty in manual materials handling industries, such as construction and telecommunications. The dangers of these regular job tasks include those of the slip and falls hazards of climbing onto the bumpers or tires of work and service vehicles in order to reach and move portable ladders to and from their racks, as well as physical overexertion and the need to hold one's body in awkward overhead postures. All of these job hazards put manual materials handling workers at risk of low back pain and musculoskeletal injuries. Lower back pain and MSK injuries attributed to manual lifting activities comprise one of the main occupational health and safety issues in Canada. The medical expenditures for lower back pain alone, according to Bone and Joint Canada, are estimated to be between $6 and $12 billion annually. Assistive devices that aid with the lifting of portable ladders on and off of work and service vans are likely to be useful in reducing the physical risks associated with the regular job duties of manual material handling workers and lower back pain and MSK injuries. A new powered and automated cargo management system called the RazerLift has been designed to assist workers in industries such as construction and telecommunications in safely completing their portable ladder unloading and loading tasks. There is reason to suggest that the RazerLift offers a viable lower back pain and MSK injury prevention strategy to such workers by reducing the need to hold the body in awkward postures with the arms and hands raised above the shoulders and head. However, previous research evidence suggests that for a variety of assistive technologies such as this one, adoption rates are low and abandonment rates are high. The RazerLift is a new powered and automated cargo management system that claims to provide consumers with increased personal safety, cargo efficiency, and improved ergonomics by providing increased cargo accessibility and flexibility, all with the press of a button. The RazerLift may offer a viable lower back pain and MSK injury prevention strategy. Although not the topic of this presentation, we also assessed biomechanical and psychophysical variables within our pilot study. Without going into too much detail, I will just highlight some of our findings that support the effectiveness of the RazerLift in reducing some of the physical consequences of manual materials handling of portable ladders from work service vans. The RazerLift reduced 3D low back compressive forces during both ladder unloading and loading tasks. The RazerLift requires lower shoulder flexion angles during both ladder unloading and loading tasks. The RazerLift was rated by participants as requiring reduced psychophysical demands, assessed using the Borg scale of perceived exertion. And use of the RazerLift to complete both ladder unloading and loading tasks requires reduced torso muscle forces compared to that required by use of traditional cargo management systems. These findings were statistically significant. The objectives of our pilot study were twofold. We will only be covering one of the objectives of our study in this presentation, which is as follows: to investigate the technology acceptance and usability of a powered and automated cargo management system, the RazerLift, used by workers whose regular job duties include those of unloading and loading portable ladders from work and service vehicles, compared to that of a traditional manual and mechanical cargo management system. It is believed that one of the main reasons why technologies are not widely adopted is because their efficacy has not yet been fully demonstrated. Additionally, technologies are often abandoned by users because of concerns over product acceptance and usability. These concerns often arise first, before concerns over the efficacy of a product. It was of our belief that researchers and product developers should assess consumer acceptance of a technology first, before resources are spent on more resource-intensive studies that can determine a product's efficacy. Because of the widespread use of other manual and mechanical cargo management systems amongst workers in various industries, we felt that assessing workers' acceptance and usability of this new powered and automated cargo management system was a necessary first step and within the scope of this pilot study. We use the Unified Theory of Acceptance and Use of Technology theoretical framework, which is rooted in the theory of planned behavior and the theory of reasoned action, which are based on the premise that if an individual intends to perform a certain behavior, it is probable that he or she will perform that behavior. According to the UTAUT theory, behavioral intention is the critical factor in predicting technology use, and surveys and perception-based approaches to measuring habit can predict intention to use a technology. There are 4 key constructs that influence an individual's behavioral intention to use a technology, and they are as follows. The first one is performance expectancy, which is the degree to which using a technology will provide the user with benefits in performing certain activities. It is tied to utility and is one of the strongest predictors of behavioral intention. The second is effort expectancy, which is the level of ease associated with an individual's use of the technology in question. The third is social influence, which is the extent to which consumers perceive that important others, including family, friends, supervisors, colleagues, etc., believe that they should use a particular technology. And facilitating conditions involve the consumer's perceptions of resources and supports available to them in using the technology to complete tasks. We used a one-way repeated measures design. Our target sample was 12, based on a target power of 0.8, an alpha of 0.5, and a large effect size of 1.2. Other studies in the area of technology acceptance and usability recommend a sample size of between 3 and 20 participants in order to obtain valid results. Other studies also recommend including 5 to 10 participants to obtain a good baseline. Due to some difficulties with participant recruitment, such as having some dropouts due to not meeting the inclusion criteria, our sample included 7 male participants between the ages of 18 and 51 years old. Our participants came primarily from construction, specifically roofing, and telecommunications backgrounds, with an average of 16.36 years of experience in their respective industries. We randomly assigned participants to complete one of 2 conditions first, before a 10-minute break, followed by completion of the second condition. Condition 1 involved the unloading and loading of a standard portable ladder from a work service van fit with the RazerLift. The second condition involved the unloading and loading of the same portable ladder from a different but identical work service van fit with a traditional cargo management system. We timed the ladder lifting tasks in seconds. Other researchers in the area of technology acceptance and usability consider the time spent on a task as a typical and quantifiable usability performance measurement. We also created and administered 2 usability questionnaires, one for each condition, to obtain a better understanding of and compare each system's acceptance by the participants. The questionnaires included 10 items answered using a 5-point Likert scale, 2 from each of the 4 key constructs and 2 assessing overall behavioral intention to use the technology. Responses to these questions were added up to obtain a total technology acceptance score, with higher scores indicating higher levels of technology acceptance. 2 more open-ended questions at the end of each questionnaire assess participants' likes and dislikes of each of the system's features. I created these questionnaires after reviewing other questionnaires developed by other researchers based on the UTAUT theory. The questionnaires were carefully reviewed by another member of our research team, considered to be an expert in this area. We determined that the interclass correlation coefficient and the Cronbach's alpha for our questionnaires were above 0.70 and statistically significant, providing evidence that our questionnaires are reliable and valid measures of technology acceptance. Here are photographs of the setup for each van with each cargo management system. The top is of the RazerLift system, and the bottom is of the traditional system. Here are the questionnaire items and the UTAUT constructs that they correspond with. These exact questions were asked of participants for each of the 2 systems tested and compared. I will pause here for a few seconds for you to read this over. Okay, so what did we find? The RazerLift was more time efficient compared to the traditional system. On average, participants completed both the unloading and loading tasks in a combined total time 31.46 seconds faster when using the RazerLift compared to the traditional cargo management system. These findings were statistically significant, as you can see here. The RazerLift was rated by participants as having higher technological acceptance overall compared to the traditional system. Participants rated the RazerLift higher for each of the usability constructs, including behavioral intention, indicating that participants would use the RazerLift to complete their ladder lifting tasks at work if it were available to them. These results indicate that participants were of the opinion that the RazerLift was more useful during completion of the ladder lifting tasks. This is performance expectancy, and was easier to use. This is effort expectancy. Participants also indicated that they felt that their boss, coworkers, family, and friends would be in favor and approve of their use of the RazerLift in completing their ladder lifting tasks at work. This is social influence. Participants regarded the RazerLift as being a better potential fit with their ladder lifting tasks at work compared to the traditional system. This is facilitating conditions. To conclude, the RazerLift is time efficient. The RazerLift has been well accepted by its users, the participants of our study. The RazerLift website's page for commercial users also includes positive comments from construction work companies that have been using the RazerLift on their work vans. The RazerLift technology is ready for more comprehensive testing of its effectiveness, beyond what we could test using our small sample size. Our biomechanical and psychophysical results support that the RazerLift may have advantages over other ladder lifting technologies, but a larger study is needed to better understand these potential advantages. Lastly, the RazerLift may be ready for more testing of its acceptance and usability in more ecological settings. Those construction work companies that have been using the RazerLift for some time could be the participants of a larger scale and more ecologically valid test of the system's acceptance and usability from workers who have actually been using the RazerLift to complete their daily ladder lifting tasks at work. So why does this matter? CAOT published a position statement on occupational therapy and workplace health in 2015. This statement outlines OT's role in the primary prevention of workplace injury. OTs have a role in providing education about body mechanics and work strategies to reduce lower back pain and MSK injuries. OTs also have a role in recommending preventative measures in order to control workplace hazards. Recommending the use of the RazerLift could prevent workplace hazards, such as having to climb on top of the work vehicle's bumper or tire, for example, in order to reach the ladder to remove it from the ladder rack. OTs also have a role in assisting employers in the development of policies, procedures, and processes that support safety at work. This could include workplace standards and policies that all workers should be using safer equipment, such as the RazerLift, potentially. Preventing workplace injuries that arise from the risks and hazards involved in manual materials handling and the lifting of portable ladders from work vans while on the job could save the healthcare system billions of dollars each year, reduce the amount of sickness and EI benefits being used, reduce the need for workplaces to have to accommodate previously injured workers returning to work following an injury, contribute to increased productivity and/or efficiency, put workers at ease and increase their sense of safety and well-being while at work, and contribute to workers' continued engagement and participation in the workplace. I would like to thank the Mitacs Accelerate program for partially funding this research project in partnership with RazerLift Products Limited. We would also like to thank Hanks Plumbing for providing us with the 2 identical vans that we needed on multiple occasions in order to make this project happen. They were very flexible and accommodating, so we thank them for that. We would also like to thank Freeze Maxwell Roofing in Calgary as well for providing us with the space to conduct our data collection. Without this flexibly available space, data collection would have been a nightmare. Lastly, I would like to thank Emily, Aaron, Daniel, and of course our research assistant Avneet for their help with setup, takedown, and data collection in general. These are the references that informed my presentation today. And I'd like to thank you for listening to my presentation. Any questions can be directed to myself at the top email there or to our principal investigator, Antonio, at that bottom email. Thank you for your time.